Thank you to everyone that's able to join. So when we go through this, I'll go question by question, identifying why the right answer is right and why the wrong answer is wrong as best as I can. So like for the multiple choice, I can easily because it's, you have the wrong answers already provided. But as we get down to later on, if you have any other products that you want to discuss, just let me know. I will ask that you put questions either into the chat or raise your hand to come off mute and ask. The only reason for that is just to prevent us all talking on top of each other. So just to make that a little bit easier. Yeah. Does anyone have any questions before we get started? Okay, cool. All right. So this is the version of the answer key that doesn't have all of the handwritten annotations, so all the modifications that were added during the grading session. That's solely so that I have more space to write. But I will try to address some of the written in comments when we get to the relevant parts later on. So if you do have questions about like the answer key itself, absolutely feel free to ask for that too. Okay, so question 1. We are trying to figure out which of the pair best fits our description. So for 1A, we are looking at what is going to be the fastest with SN1. So for SN1, remember that it just cares for the substrate. It cares about carbocation stability. That's the key factor for that determining the rate. So when we look at that, so carbocation stability and leaving group ability, those were the two things that controlled our rate. Because our leaving groups are both bromine, they're exactly the same, then I'm not looking at the leaving group ability, I'm just looking at carbocation stability. So for our carbocation stabilities, remember that it is that benzylic is better than allylic, which is better than aliphatic, which also follows within each of those that tertiary is better than secondary, which is better than primary. So then that's of those. And again, tertiary is better than secondary, is better than primary, and then tertiary is better than secondary, is better than primary. So that's what we're looking for here, is we're looking at the stability of the carbocation that would form. So when I look at these two structures, I see that this one is on benzene. So remember that benzylic means that you are one away from benzene. That is benzylic. This one would be on benzene, on the double bond itself. That is phenylic. It just means it's on the benzene itself. That is unstable. We are not going to make a carbocation on an sp2 hybridized atom. So the fact that it is directly on the double bond, that is unstable. That is definitely going to be the wrong answer. So anything would be faster than that for SN1. And then when we look at this one, we see that it is tertiary. Come on, tertiary aliphatic. It is tertiary because it is connected to, so the alpha carbon is connected to 3 other carbons. And then also the fact that it is, there are no double bonds next door, that's what makes it aliphatic. So there's no resonance. The allylic, just to, I guess, clarify that one as well in case there was confusion. The allylic is where you're one away from the pi bond, one away from an alkene. And the key part of why being one away is so important is because you get resonance. So that's the big difference. So aliphatic is just our normal alkanes. These have resonance. This is no resonance. That's why the benzylic and allylic are more stable. But if you're on the double bond directly, that's not benzylic, that's not allylic, that is unstable. So then we do the same consideration for 1B. Here, I see that they are both, again, the same leaving group. So leaving group ability didn't come into play here. So then I'm going to look at my substrates, and I do not see any pi bonds. There are no double bonds. There are no triple bonds. There's no benzylic or allylic possibility. So I'm just looking at straight aliphatic. So for this, I'm just looking at tertiary versus secondary versus primary. This one, this alpha carbon is attached to 3 other carbons. So that is tertiary aliphatic. This one, this carbon is attached to 1 other carbon. So that is primary aliphatic. So tertiary is going to be more stable. The reason why tertiary is more stable than primary is because of our hyperconjugation and induction. So remember that hyperconjugation, that is the delocalization of electron density through space. So that was from that sigma bond to the empty p orbital. And then induction is going to be through the sigma bond itself. So that's why they kind of work in concert together. Like they work together to say that the carbocation that would form, so if this leaves and you just get a positive charge there, I have 3 things, 3 carbon groups donating in, whereas here I only have 1. So that's going to be very unstable. So having more substituents makes it more stable because there's more electron density being donated in to stabilize it. And the question of, will the annotated version be posted as well? Yes, that'll get posted as well. Okay. We're looking at 1C and 1D. That's looking at our E1 reaction. So for E1, remember that it has the same considerations as SN1 because the slow step is still just carbocation formation. So for our E1 reaction, the rate only depends on carbocation stability and leaving group ability. So when we look at these, I again see they are the same leaving group. So I don't have to worry about my leaving group ability. And so then I'm just looking at the substrate factors. This is going to be 1 away from my double bond. So this is allylic. And because it's attached to 2 other carbons, it is going to be secondary. This one is on the alkene directly. That makes it vinylic. And just like that phenylic, being on the double bond directly, being right on that pi bond, that is unstable. That is not going to be a stabilized carbocation. So that is going to be the wrong answer. And anything would be more stable than that. Anything would be faster than that. And so this one is especially stable because it's going to be stabilized via hyperconjugation, induction, and resonance. It has all 3 factors helping to stabilize that carbocation here. Looking at 1D, this is the same consideration as 1B. So there are no pi bonds. We're just looking at our aliphatic substrates. It is at tertiary versus the primary. Tertiary is the more stable carbocation. So that is faster in an E1 reaction. When we look at 1E, we're doing the same consideration, but now for SN2. So for SN2 with our substrates, remember SN2, it will have that leaving group ability. It will also have the steric factors. And it has the nucleophilicity. So those are the things that affect the rate of our SN2 reaction. So the first 2 are related to our substrate. The nucleophile is not even mentioned here. I'm just looking at my substrates. I know I'm looking at substrates because I have a good leaving group. So that's telling me that these are the electrophiles. And so that's what I'm comparing, is I'm comparing electrophile strength, recognizing that that's the good leaving group. And I get that polarized bond. I get that delta positive. that's what's indicating to me that this is my electrophile. So I'm really just looking at leaving groupability and sterics, not nucleophile strength, because I'm not going to be comparing these in terms of their nucleophilicity, because they're not good nucleophiles. They're good electrophiles. So for this, for our sterics, there are two things to note. Or I guess for our substrate, there are two things to note. With sterics, we're saying that it has to be primary is better than secondary, and we are not going to have it happen for tertiary. And actually, I guess I should have highlighted the fact that the primary aliphatic is the one that doesn't work for SM1 or for E1. So the difference here is that we're saying primary is better than secondary, which is better than tertiary, and the tertiary we say doesn't happen because it's too sterically encumbered. So that's why that substitution pattern doesn't work. The other thing that we need to take into account for our SN2 reaction is that it only works on sp3 hybridized carbons. The reason why it must be sp3 is because this orbital is going to be a little bit larger than my sp2 hybridized orbital. So sp2 has less p character, meaning I have fewer p orbitals added in. So I only had 2 p's as opposed to 3 p's. So it has less of that dumbbell shape, like it's less distorted coming out. So that means I'm going to get a stronger bond. So the stronger bond is going to be harder to break. That's going to make it slower. So for SN2, for SN2, we say that it doesn't work on the sp2 hybridized carbon, not because of carbocation stability, but more so because of bond strength. So it's because of the fact that this bond is very strong, and so it's hard to break. So we do not do SN2 on an sp2 hybridized carbon because our bond is too strong. Also, it is a little bit harder to access that sigma star just because of that pi bond that's happening above and below. So if we try to draw the orbitals, let's see if I can try to draw it without it looking like a total disaster on this. So if here is my p orbitals. So this is where I have electron density. And then I also, and that's straight up and down. And then on my sigma bonds, I have the sigma orbitals, or sorry, the sp2 hybridized orbitals. But the one that we care about is accessing that sigma star for the carbon leaving group bond. So for this one, that is the sigma star we're trying to access. This sigma star is just a little, it's really hard to see on this. I'm so sorry. It's a little bit closer and not overlapping, but it's closer to the electron density of the pi bond that's formed. So it's closer to that p orbital just a little bit. So that together with the sigma bonds is really kind of making this harder to access. So there's the two factors there. One, the sigma star is harder to access because of the increased electron density that's going to be repelling it all around from the p orbitals and the sigma bonds from the sp2 hybridized orbitals. And probably more significantly is that carbon leaving group bond is going to be stronger, so it's harder to break. So that's why we are not going to do this one. So carbon leaving group bond is stronger with sp2. So that's why it's not going to happen on that structure. So just like with the other ones, literally anything would be better than this structure. So has to be the other one. But I also know this one is going to be correct because it is that sp3 hybridized and it is secondary. So that is saying that this is going to be allowable. It is secondary and sp3 that together makes it possible for that SN2. Looking at my next one, there are no hybridization effects to worry about. We are just looking at tertiary versus secondary, tertiary versus primary. Primary is going to be my fastest. It has the least amount of sterics. Sterics is really the only factor here. box this off, that was the note there. So because of sterics, that's why primary is better than the tertiary. I can't get to that carbon in order to have my nucleophile attacked. For E2, our rates depend on our leaving group ability, the number of beta hydrogens, right? That's why the substituents were that tertiary was better than secondary, which is better than primary. So this is where it deviated and was the total opposite order because it was the number of beta hydrogens. And it was also based on our base strength. So again, I know that these are not going to be bases. I know that they are my electrophiles or potentially acids. So then that's all we're really going to consider. E2 can happen on an sp2 hybridized carbon. This was the only mechanism that did work on sp2. So our SN1, E1, and SN2, all three of those do not work on sp2 hybridized carbons directly. E2, totally fine with with sp2, because I will be able to get that anti-periplanar alignment. It's actually locked into an anti-periplanar alignment. So E2 is okay with SN2, or sorry, sp2, sorry. Too many two words. So that E2 mechanism is okay with an sp2 hybridized carbon, because you just got to make sure you are anti-periplanar and the orbitals align here. So that works. So what we're looking for here really is number beta hydrogens. That's really our only consideration between these. So for the structure on the left here, there are 0 hydrogens to the right. There are 3 hydrogens to the left. Wait. There are 3 hydrogens to the right, 0 hydrogens to the left. On the structure on the right here, there's 0 beta hydrogens. So this cannot react. It cannot do E2. This substrate can't do it because there are no beta hydrogens. If you don't have beta hydrogens, you can't do the elimination. So this one is going to be faster because it does have beta hydrogens and it has 3 to play with. For 1H, looking at the fastest with E2, for this one, again, we are the same leaving group. We're not doing a base. We're looking at our electrophiles. So we're looking at the substitution pattern. And we see here that I have 1, 2, 3, 4, 5, 6, 7, 8 beta hydrogens. Here, I just have 2 beta hydrogens. So the one with 8 is going to be the one that's faster. Having it be tertiary gave me more beta hydrogens. That makes it the faster E2 elimination. The one on the right being primary, although possible, it can do E2 because it has beta hydrogens. It's going to be slower because it doesn't have as many. All right. Are there any questions about the substrate ranking effects for SN1, E1, SN2, or E2? So then the right-hand side of this, looking at most nucleophilic, remember that our nucleophiles and base trends generally align, that our good bases are usually good nucleophiles. Our deviations are when you're looking at sterics. So the if sterically encumbered, or let's just say it this way, if bulky, then you're base only, not a nucleophile, because nucleophiles care about the size of your whole molecule. It needs to be able to get at that site, at that carbon. So if you are bulky and sterically encumbered, then you're only going to be a base. You are not going to be a nucleophile. And then our other deviation is that if you are the conjugate base of our strong acids, then you are a nucleophile, not a base. Because now you are too stable as a base, but you're still anionic, so it's still favorable for the nucleophilicity. So when we just think about our general base ranking trends, which I guess I'll put down here, we looked at charge first, then atom. Within atom, we said that there was size and electronegativity. Then we looked at resonance, induction, and hybridization, and we looked at that in that order. So looking for the good nucleophile, both of these are small molecules. So there aren't like a lot of carbon atoms, they're not tert butyls. So they're going to be small. So that both are capable in terms of being nucleophiles and bases. So then really we're just going to use our base ranking chart to say negative charge, better nucleophile. So that's why the negative is going to make it a better nucleophile. It is more electron rich. You have a greater concentration of electron density, greater concentration, more localized, better nucleophile. That anion makes it the better nucleophile. Being neutral, although it still can be a nucleophile, it is not as good. Most basic. So for this, we're just straight up using our Caryo or Carya ranking. So when we look at these, they have the same charge. They are both negatively charged. So next I go to the atom. The atom that is most electron rich is comparing that nitrogen to that oxygen. This nitrogen is going to have, so there's a difference in the atom. They are in the same row or same period on the periodic table. So that means we're taking electronegativity as the factor. So if you're in the same row, you use electronegativity. Being in the same row, you want the less electronegative atom is going to be the one that's more basic. So nitrogen is less electronegative. So that makes it the better base than oxygen. And that's just saying that it is going to have the electrons are going to essentially be farther from the nucleus. They're not being pulled in as tightly, so they're going to be farther out. Looking at base only, so where we become a weak nucleophile is going to be that sterics. So when I look at this, I see that tert butyl, that is bulky. That cannot be a nucleophile, so that will be a base only. Also, I see that sodium sulfide, that is going to be a strong nucleophile. So that's definitely the wrong answer there. The sulfur is highly polarized was the issue or the rationale there. Sulfur is highly polarized, so it's going to be just very reactive, really good at reaching out and attacking carbon. Nucleophile only, weak base, is going to be that conjugate base of our strong acid. Negative. This is neutral. This is the conjugate base of a strong acid. I'm just going to write of HA for space. So of our strong acid, strong bronzed acid. So that's definitely going to be a nucleophile only. That chloride is not going to be a strong base because it makes HCl. So actually, we'll just make it HCl and have it be fully accurate. Sodium hydride, this was actually base only. And that was because of kinetics. So acid-base chemistry is fast. And it makes hydrogen gas. So the reaction that happens really quickly happens irreversibly. So that's why our sodium hydride, just naked H minus, is always a base only. It'll never be a nucleophile. 1M was going to be faster with my tertiary leaving group. That is E2, for the reason we already said, was that number of beta hydrogens. That's what made E2 faster with the tertiary. SN2 cannot happen with a tertiary because of sterics. So SN2 is definitely the wrong answer because of sterics. So this is slower because sterics. This is faster because of more beta hydrogens. When we consider temperature, then at room temperature and heated, E2 eliminations are faster. So room temperature is approximately 20 degrees Celsius. So anything above 20 is hot. So heat favors the elimination. It is giving it enough energy to overcome the energy of activation barrier, and is also going to help funnel down to the more stable product, forming that carbon-carbon double bond is pretty stable. So that's going to make that alkene. SN2, our substitutions, they prefer colder temperatures. So if it was 0 degrees, then SN2 would have been faster. And being at the colder temperature is going to allow for a more organized transition state. So it's allowing your nucleophile to actually get to your electrophile and be aligned right away, instead of just doing whatever's fastest and trying to grab that hydrogen and just react right away. Being cold is giving it time to get aligned to do the substitution. 1O, looking at a reductant. Remember that reductants are increasing the number of bonds to hydrogen or decreasing the number of bonds to oxygen and or. So when I look at this, potassium permanganate, that has a lot of oxygens. That's going to be increasing my number of bonds to oxygens. That's one of my strong oxidants. In fact, the strongest oxidant, come back, that we've learned about. The Grignard is going to be adding carbon-carbon bonds, which is essentially that carbon-hydrogen, and it is usually added into carbonyls, so it's going to be reducing the number of bonds to oxygen. So that is absolutely going to be a reductant. So potassium permanganate is just an oxidant because it increases number of oxygens. Grignard is going to be a reductant because it's increasing the number of bonds, well, to carbon, but it's decreasing the number of bonds to oxygen. Protic solvent is going to be something that has a delta positive hydrogen. That's what makes it protic. So when we look at this, this hydrogen is attached to the oxygen atom, which is electronegative. That is a delta positive hydrogen. It's the alcoholic solvent. That is a protic solvent. CH2Cl2, that is this thing. That is dichloromethane, DCM. That is our aprotic solvent, because these hydrogens are attached to carbon. Those are nonpolar bonds. All right. Any questions about number 1? All right, cool. Number 2. This should look really familiar. This is modified from one of your quiz questions. So what is the rate determining step in the reaction between 2-methylpropan-2-ol and hydrobromic acid? All right, so we got to figure out what reaction is happening. So 2-methylpropan-2-ol. So prop is 3 carbons and tells me all single bonds. Ol tells me I have an OH. That 2 tells me it's on C2. The meth tells me I have a 1 carbon. Ol tells me a substituent. That 2 tells me that that is on C2 as well. So that means that this is my 2-methylpropan-2-ol, also known as tert-butanol. And I'm reacting that with hydrobromic acid. That is going to be an SN1 reaction. So that's what I'm looking for, is SN1, because this is going to be tertiary. And once this protonates, so you have a strong acid, you protonate something, you protonate your alcohol. Remember that acid-base chemistry is always fast. That'll never be your slow step. So that's going to happen very quickly. Then you get bromide. Bromide is that nucleophile only. So we're going to then, so that's looking at SN2 versus SN1. Tertiary leaving group is going to then be SN1. So that's how I knew it was SN1. So I'm looking for my slow step in SN1 is going to be formation of my carbocation. So I'm going to look for the step that is describing the loss of the hydronium ion to form a carbocation. So when I consider these options, I have ionization of the alcohol to give a carbocation. No, because remember, we are never going to straight ionize that OH. That OH is a bad leaving group. So we are not going to just form a carbocation directly. Loss of water from the protonated alcohol to give us a carbocation. Yes, that is the correct answer. That is exactly the slow step. That is describing that we already have the good leaving group, the protonated alcohol, and that is leaving to give our carbocation. So yes, that is the slow step of the SN1 for this reaction. Displacement of water from the protonated alcohol by the bromide. This would be true if it was SN2. So that's describing that displacement of your leaving group by your nucleophile. That's saying it's all in one go. That is an SN2 reaction, so that is incorrect. Capture of the carbocation by the bromide. This is your second step of our SN1 reaction. That is going to be fast, so that is not the correct answer. And then protonation of the alcohol, this does happen, but again, acid base is always going to be very fast. So that will never be our slow step either. So the rate determining step is forming the carbocation. Any questions about 2? Question 3, which of the following halides will react most rapidly with SN2 in an aprotic solvent? Okay, so we got to pay attention to our solvent here. So remember that in an aprotic solvent, that our leaving groups are just going to be the weak bases. Those weak conjugate bases is our general trend. So whatever's going to be the weakest conjugate base is going to be the best leaving group. So my weakest conjugate base, I'm comparing that chloride to the bromide to the iodide. The iodide is the largest because I'm comparing elements in the same group, in the same column. So I'm using size. The larger you are, the more stable you are, the weaker you are as a base. That's why hydroiodic acid is our strongest acid. So of the halogens. So iodine is the largest atom. So in an aprotic solvent, that is going to be my best leaving group. In a protic solvent, chloride would be the best because chloride is small and you get that tight solvent shell. So the solvent shell impacts that, where the smaller atom is now my best leaving group because the solvent shell will block it and stop it from reacting further. But aprotic solvent, we're just looking at our normal conjugate base trends. So its size was the impact there. Any questions about 3?
We're comparing size because it's in a column, is what you said?
Mm-hmm. Yep, that's correct. Right, number 4. This was directly out of the one of the quizzes. So a reaction between 1-iodopropane and aqueous sodium hydroxide. So again, we need our structures. So I have an iodine on carbon 1 of a 3-carbon chain, sodium hydroxide, NaOH. Aqueous means in water. So I'm trying to figure out what is the reaction going to be. Well, sodium hydroxide, that is a strong nucleophile, strong base. I see a primary leaving group. That tells me SN2. So strong was SN2 or E2. Primary was SN2. So I'm looking for nucleophilic attack of that hydroxide ion. So that is the correct answer. Actually, I didn't even have to worry about that here because I don't even have base deprotonating. My only options are nucleophilic attack or electrophilic attack. Electrophilic attack, not a thing. Remember that our electrophiles get attacked. They are not going to do the attacking. So these are wrong because the electrophile gets attacked. It doesn't have the electrons to do the attacking. So it would have to be nucleophilic attack. And when I compare to this one, sodium ions, that's Na+, that also doesn't have electron density. So that is not going to be able to be a nucleophile. It's not electron rich. If anything, it's electron deficient. So that is definitely not going to be our nucleophile. Any questions about 4? Number 5, again, this came directly out of your quiz. What is the major product of the following reaction? All right, so I see potassium hydroxide. So I see that OH minus. That tells me it is a strong nucleophile, strong base. And then I see my thiol. The thiol, this is a bad leaving group. So that is not going to be an electrophile, but it is acidic. That hydrogen is acidic. Remember that hydrogen is acidic. It's on sulfur. Sulfur is a larger atom. That's going to make it more acidic. So the first step is just that acid-base reaction that forms the S minus. Now this is a strong nucleophile to react with my electrophile in step 2. So in step 2, I'm adding that bromomethane that is going to be doing an SN2 reaction. So I'm going to look for a structure that has 4 carbons, then sulfur, then 1 carbon. So that is option B, where I see that 1, 2, 3, 4 carbons, sulfur, and then another carbon. So this would have required us to attack. Actually, there's no way to make this. There's no way to have this like group break off and then also have the this become a CH3. There's no way to have that methyl and the sulfurs there. So carbon's not a good leaving group. No way to do that. For C, I see that there are 1, 2, 3, 4, 5, 6 carbons. That is way too many. I don't have that many. So remember conservation of matter. I can't have more elements than just what I have. I only have a total of 5 carbons to play with. C is incorrect. Too many carbons. Besides the fact that also oxygen should not have been incorporated. It was only acting as a base. And we would be lengthening the carbon chain on a side that doesn't have a functional group, essentially. So like there's many reasons why that's wrong, but the first immediate thing I would have hoped you would have seen is way too many carbons. For D, this is essentially the equivalent of B, except with oxygen. This would have been assuming that you did 2 SN2 reactions. But the problem is that first step, that sulfur was a bad leaving group. Just like how hydroxide is a bad leaving group, sulfide's a bad leaving group. So we're not doing SN2 twice. We're doing acid-base chemistry and then SN2. Any questions about number 5? Number 6, which reagent is best to exclusively produce the given product? All right, so we're looking at this and we are seeing that I have alcohol that needs to directly turn into a bromine. So I'm going to, 1, make sure that my reagent contains bromine. When I look across, all 4 of these do have the element that I need. So that didn't really help me any. Next, I'm going to recognize the inversion of stereochemistry. That tells me SN2. So I need to do an SN2 reaction. And Br2, not going to be a good nucleophile. We're looking for something that's going to be a good nucleophile. And we also need something that's going to turn that alcohol into a good leaving group, because right now the alcohol is a bad leaving group. So this sodium bromide is not going to work because alcohol is a bad leaving group. The HBr, that can turn it into the desired product, but there is competition with SN1. So being on a secondary carbon, you could also form a carbocation and get racemization. So that's why B can do the reaction, but it's not the best. The best is our phosphorus tribromide. That's the one that will exclusively produce this product because it will only react via SN2. And it's very good at turning an alcohol into the good leaving group for the SN2 reaction to be promoted. Any questions about 6? Number 7, which reagent is best to exclusively produce the given product? All right, again, we're looking. I now see that I have a good leaving group. That OTS, that's that tosylate, that's that sulfonate. So that's a very good leaving group. So it looks like this. So you get the sulfur with the 2 double bonds to oxygen, benzene, and a CH3. So that's our TS, the OTS. So what that equals. So that's a very good leaving group. And so then we're going to look to see, again, I see that inversion of stereochemistry. So I again need to make sure I'm doing SN2. So I want something that's going to be just a really strong nucleophile. I want my strongest nucleophile. That's going to be that Br minus. Being anionic makes it the strong nucleophile. HBr is, again, not the best because it could potentially lead to carbocation formation, because once you protonate it, you can have that carbocation formation on the secondary leaving group. So this has mixed with SN1. Br2, again, it's just not a nucleophile, so that doesn't work. And our phosphorus bromide, that was working when we had alcohols to our halogens. I have an OTS, not an OH, so just straight up sodium bromide is the best reagent here. Any questions about number 7? Number 8. What is the major organic product from the following reaction? All right, so I see that tert-butanol, hydrochloric acid, methanol, and it is 0 degrees Celsius. So I see that I have strong acid. So strong acid is going to protonate something. So when I protonate my alcohol, and I consider what's in solution, when I look for, so I know this is my electrophile, sorry. So between these two, the question is, which one's the better nucleophile? So you might be tempted to think chloride because of the anion, but remember, we got to watch out for a solvent shell. Methanol is a protic solvent. Chloride is not a nucleophile in protic solvent. It's too small. You get a tight solvent shell, it is not good at locating anything. So that means methanol is my nucleophile. So methanol is weak. So that tells me SN1 or E1. My leaving group is tertiary. That again tells me SN1 or E1. Cold is what tells me SN1. So I am looking for the product that is SN1, where I'm replacing my OH with my nucleophile, the OMe. That is why that is correct. A is incorrect. That's assuming that there's no reaction. C is incorrect because of the chloride is not a nucleophile and protic solvent. And then D is incorrect because of the temperature. So this would have been an E1 reaction, and we are cold. So if it was room temperature or heated, then that would have been the product. Any questions about number 8? Number 9 also came directly from the quiz. When R3-bromo-3-methylhexane is treated with water, a racemic mixture of that alcohol is produced. By what mechanism does this occur? Racemic SN1. Seeing that racemic word immediately tells us it had to be SN1. SN2 would have been inversion of stereochemistry. E2 would have been making an alkene. And E1 also would have been an alkene. So we don't describe those as racemized. when describing the alkenes, we had our Zaitsev, Hoffman, E or Z. We didn't get to use racemic. Racemic means you have R and S. So that right away told me B was the correct answer. Any questions about number 9? Number 10. Rank the following alkenes in decreasing order of stability. So for our alkenes, we need to remember that first, we consider our number of substituents. Then we consider sterics. So that tells me my tetrasubstituted is going to be more stable than trisubstituted, which is more stable than di, which is more stable than primary or mono, sorry. And then within the substitution patterns, then your trans will be more stable than cis, which is more stable than 1,1 disubstituted, and E is going to be more stable than Z. So when I look at this first one is mono-substituted. Next one is a 1,1 disubstituted. Next one is cis disubstituted, followed by trans disubstituted, then my tri-substituted, then my tetra-substituted. And again, I'm just looking at the number of groups that are coming off, the number of non-hydrogens attached to my double bond. So tetra is definitely going to be number 1. It has the greatest number of substituents. Then tri becomes number 2. Then my disubstituteds are going to be 3, 4, and 5. And mono has to be number 6 as the least. So then within my disubstitutes, I'm now going to consider my sterics, where my groups are as far apart as possible with trans. That is going to be the next most stable. Then cis is now going to have some increased sterics, but at least they are on separate carbons. When I am 1,1 disubstituted, that is the greatest amount of sterics. These are even closer together, so that is the least stable of the alkenes. Any questions about number 10? Number 11. Rank the following alcohols in decreasing order of reactivity to acid catalyzed dehydration, E1 reaction, where most reactive, least, okay, whatever. E1, we're looking at carbocation stability, right? So for these, again, they are all going to have the same potential leaving group. The acid catalyzed is telling me that we're going to protonate the alcohol. Dehydration says that we're going to lose water. So we're going to end up losing that protonated alcohol and it'll be forming the double bond. So with these, that E1, we're just looking at carbocation stability. Again, benzylic is more stable than allylic, which is more stable than aliphatic. And then you consider your tertiary is more stable than secondary, which is more stable than primary. Consider resonance first, and then your hyperconjugation and induction. So this first one is secondary and benzylic. It is right outside the double bond. That is going to be number 1. The next one is secondary and allylic. The next one is primary allylic. Then I have my tertiary aliphatic. Then secondary aliphatic. And then primary aliphatic. So when we look at this, benzylic is going to be greater than allylic or aliphatics. So I know that this one has to be number 1. And then 2 and 3 are here. And then 4, 5, and 6 are off to the right. So then within my allylics, now you're going to compare secondary versus primary. Secondary is better than primary. Then tertiary is better than secondary, which is better than primary. Any questions about number 11? On the structure below, draw in our necessary molecular orbitals for an SN2 reaction and then briefly describe what's going on. Okay. So for number 12, we need to be able to access the sigma star so that I can break my carbon leaving group bond. Remember that the anti-bonding orbital is what is necessary to break bonds. So I just need you to draw in that sigma star. So that sigma star is created by the overlap of my sp3 hybridized carbon and the p orbital from the chlorine. So when I have that, or it's actually the repulsion of it. So they are mismatched phasing because I need it to be the antibonding orbital. So then these are going to repel each other. So I get big, little, little, big, where my shading alternates. And then that is the sigma star that you need to draw in. If you drew in the N orbital for the nucleophile or that arrow, the arrow isn't necessary. None of this was graded. If you drew it in, cool. If you didn't, whatever. I was just looking for the sigma star. That's what's necessary in order to do my SN2 reaction. I need to access that sigma star. So it was 1 point for having the big, little, little, big, and then 1 point for having the correct shading alternating. It didn't have to be that shaded. It could be the other way. Like this could be shaded, unshaded, shaded, unshaded. I just need the alternated shading. For the open-ended word part, the rationale as to why we see inversion of stereochemistry is because we need to be able to access the accessible part of my sigma star is on the backside or 180 degrees from that leaving group. So remember that your sigma orbital, the sigma that results, what color? I'll do purple. So the sigma that results from this is going to be this little, big, little. That is occurring on top of, can I not do it on top? Okay, well, whatever. It's happening on top of my antibonding orbital simultaneously. So the part of it where I can access the open part is going to actually be, and actually this isn't even a good drawing because it actually continues out a bit more. Because your nuclei are going to be, they're there and there. So it's going to be there and there for that orbital overlap. So it comes out a little bit more. Yeah, whatever. This is where the electron density is. So the accessible portion is on the backside, on the opposite end of where your leaving group is actually located. Any questions about number 12? That looks like a disaster, so leave it that way. Number 13. So I was hoping two things with number 13. One, I was hoping that you would see that I told you that this structure can never go to this structure. So I was hoping that then when you got to the predict the products, you then knew that you could never draw that structure, the product in 13 on your predict the products, because I told you this thing will never exist. So that was one thing that I was hoping was going to be a hint to make life easier. Also, if you forgot what PR stood for, propyl is that, so Me is methyl. That's your CH3. Your ET is ethyl. That's your CH2, CH3. PR is propyl. That's CH2, CH2, CH3. And then Bu is butyl, which is CH2, 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 CH3. And I was hoping that even if you forgot what PR was, I gave you 3 carbons here. So I was hoping that that also reminded you what propyl was. Especially since I didn't have a lot of space to kind of draw this out on the predict the products. I was hoping that that was going to help you out as a reminder. Also remember with our line diagrams, the methyl here is what is capping the end of that line. So with our line diagrams, we assume a carbon if nothing is written. Otherwise, at the end of the line, whatever's written is what's there. So the line diagram without the capped methyls would be this. Is that structure. Telling us that that's just a CH3 at the end of that line. Okay, so to the actual point of the question, we're trying to say why it is not going to be possible, regardless of our base chosen, to make this product. Why can't I make this product? And you must discuss why it doesn't work for both E2 and E1. So for E2, why I can't make this product is because the hydrogen is not antiperiplanar to that leaving group. So the identity of the base, although it does matter, you can't have a bulky base, you would need a non-bulky base, but I'm assuming you have the correct base when or like the potentially correct base when you're trying to get to this specific thing. So if you talked about the fact that a bulky base couldn't get in there to access this hydrogen, cool, that's true, but that was ungraded. So what was more important was that even if you chose hydroxide, you chose the base that theoretically will get in at that proton, you must have the antiperiplanar alignment. Right now, they are aligned with each other. You would have to do the rotation if you have that NaOH to actually get you to, oops. Okay. So my fluorine is here. I need my wedge to go to my dash because I need the hydrogen on the dash. So wedge went to dash, dash goes to line goes to wedge because I just want to rotate that carbon. So when I do that, that is going to make this alkene, which is the E alkene. This is Z. So we are unable to do it because in E2, it must be antiperiplanar, and the antiperiplanar alignment with that starting material leads to the E alkene. So that's why that structure cannot lead to that product in an E2 reaction ever. In E1, I also know that it is not going to work because with E1, you are always going to make your large groups as far apart as possible. So E1 is always going to lead to the E alkene because of that carbocation intermediate, because you go through the carbocation that is going to get your large groups as far apart as possible. That's what makes the E alkene. So I was looking for you to identify that you needed your big groups as far apart as possible, which is not what's happening in the product that's given. So that's why it's not possible regardless of the base that you choose. Any questions about 13? Cool. 14. Draw the transition state for the slow step. All right, so we got to figure out which mechanism we're doing. I see that I have inversion of stereochemistry. So first of all, I went from one functional group to a different functional group. That's substitution. So I know it's got to be substitution. And then I see that I have inversion of stereochemistry. That tells me SN2. So I'm looking for the slow step of SN2. That is where my nucleophile is actually attacking and kicking out the leaving group. It's the step. So the slow step is the only step. So I know that I'm doing SN2. It says to assume that I am exothermic. All right, so if I'm exothermic, that means that my products are going to be lower in energy than my starting materials. So that means that my transition state is going to be an early transition state, which means that it looks more like my starting materials, because that's what it's closer in energy to. So I need to make sure that I have my correct structure happening. I need the leaving group and my nucleophile to be in line with each other, to be 180 degrees. So it needs to be on a straight line in order to illustrate that. So I actually had to rotate the structure to get it to that point. And it didn't matter if it was like straight up and down or left and right, or even on an angle. It had to be shown that it is that straight line. So you had to rotate your structure in order to get it so that this is in a straight line. So it is 180 degrees from each other. then we would recognize the partial bonds that we are forming are only going to be between the hydroxide and your leaving group. So remember that sodium hydroxide dissociates into Na plus and OH minus. So there are no bonds there. Your starting materials are OH minus and this thing. So there is no sodium being drawn in our transition state. If you wanted to, you could draw it in as just Na plus, just chilling by itself, because it keeps the formal positive charge, but it's not actually involved in the transition state. So those are the partial bonds. You need to have it only to the hydroxide in the leaving group, the tosylate. And then we needed to have our partial negative on the OH only, because the early transition state tells me I need to look like my starting materials. The only thing with the charge in my starting materials is that hydroxide. So when it has that partial positive or the partial negative, when it has a formal negative, it gets the partial negative in the transition state. And then, so it's the only thing with the charge there. So it's the only thing with a partial charge there. The OH is going to be long. The OTS is short, because with our short and long, long is going to be for the bonds that don't exist yet. Short are for the bonds that do exist yet already. So when I look at this, in my starting materials, the bond that I have is the carbon leaving group bond, short. The bond that doesn't exist yet is that carbon hydroxide bond. So that one is long. For our 1 point for the given starting material, you had to make sure that you had that the 4 carbons. So you recognize that it was the ethyl, carbon, methyl. If you used abbreviations like I did, cool. If you drew it out, cool. You just needed to have that structure. And then the backside attack, illustrating that it was 180 degrees. That was to get that last point. Any questions about 14? All right, find the error. So for to find the errors, there isn't much of an explanation. Well, we'll talk about every one of them. So we're trying to identify the primary error. So I'm asking you to not only assess like everything that could happen or everything that's potentially going wrong, but what is the biggest issue with this? Where is the greatest mistake that is occurring? Like in terms of what are those like reagents trying to do? Like what is the biggest issue here? And so I said no more than 10 words per answer, just as a point of trying to get you to not write novels, and so you don't spend too much time on any 1 3-point question. Complete sentences were not necessary, and be as clear as possible. My intent there was to, I guess what I should have said was be as specific as possible, in that illustrate to me that you fully understand what the error is. I want you to tell me what is wrong with this. Like, what is the actual issue with this? So for 15A, what I see is I'm trying to do the Williamson ether synthesis. I'm trying to go from an alcohol to an ether. So I'm trying to do a substitution reaction. I'm trying to do SN2. The first step, sodium hydride, that's just a strong base. That's just going to do acid base. That makes my O minus. And then I'm trying to do an SN2 reaction, but I cannot do SN2 with a tertiary leaving group because it's too sterically encumbered. So if you went on to talk about the fact that it's sterically encumbered and went into that why, then awesome. That means you fully understood it. But what I was looking for as a complete answer for identifying the error is the fact that SN2 does not work on a tertiary leaving group. So if you said no SN2 with tertiary, then that got you the 3 points, the full credit. I'll probably do these one at a time. Are there any questions about A? For, we'll go to the right. For B, looking at this, I see that I have sulfuric acid. Sulfuric acid, we got to protonate something. We are doing our opening of our epoxides. That means that we're going to need to pay attention to where our nucleophile adds, and it's either going to be an SN2 or an SN1 type. So the fact that it's a strong acid told me SN1 type. So then that was saying that I needed to have my ethanol end up on the more substituted side because it was the SN1 type. SN1 type is following the electronics. So then if you identified that with these reagents, you needed to have the opposite regiochemistry, the fact that you're SN1 type because it's a strong acid, you're attacking the more substituted side, then that was full credit. Or if you identified it as the reagents were wrong. So if you said that these reagents are incorrect and the error is that you needed to have your ethoxide to do SN2 to get the less substituted side, then that also received full credit. Yeah, any questions about B? C, we are looking at how we're doing a substitution reaction. So we have a strong nucleophile, that OH minus is strong nucleophile, strong base. So if we're doing substitution, that tells me I'm trying to do an SN2. So then it is the fact that I can't do SN2 on an sp2 hybridized carbon. If you got into the fact that, you know, the why it doesn't work is because of you have a harder time actually accessing that sigma star. So that's a big issue in this one, specifically wrong structure, because your sigma star is pointing directly into the benzene. Or if you had said that it was no SN2 because of the fact that this is a really strong carbon leaving group bond. That was awesome, but I was just looking for just what is the error? I cannot do SN2 on an sp2 hybridized carbon. All right. Any questions about C? D. Here we see our ketone with lithium aluminum hydride. So this is going to add H minus in a protic solvent. That is correct. And I do see my acid workup. So that is correct. That will add that hydrogen from the acid workup. So then the error is that lithium aluminum hydride is adding a hydrogen, not an ethyl. So I was looking for you to identify that the elements or the groups were not correct. So if you said that it needed to be hydrogen, not ethyl, then that got full credit. If you just said, you know, ethyl is wrong, then that only received partial credit because you didn't tell me like the actual error is that lithium aluminum hydride does not add ethyls. Like that's the problem, is that lithium aluminum hydride is adding hydrogen, not ethyl. So that's what got it complete. Or if you said that you needed a different reagent, so specifically saying the ethyl magnesium bromide, or if you said your ethyl lithium, then that also received full credit because that was recognizing that you needed a different reagent in order to get to that product. Any questions about D? E. So for this one, we are adding a Grignard into an aldehyde. So remember that when we go from an aldehyde with a Grignard, we're going to end up with a secondary alcohol, or in this case, alkoxide. But it's secondary is the key thing. So the fact that I don't have an acid workup, that means that it is correct to still have the magnesium bromide attached to the oxygen. The ET, that ethyl, that 2-carbon chain, is being added here. There's my 2-carbon chain. That hydrogen, although implicit, is still there. So this hydrogen was there. A lot of students were saying that the hydrogen was missing. The hydrogen isn't missing. It's just implicit. So the actual error is the solvent is not compatible. So I can't have that protic solvent with my Grignard because Grignards are a strong base. So if you recognize that the ethanol was a protic solvent and you can have a protic solvent with it, then that received full credit. if you just like circled the solvent, then that got you 1 point because it didn't say what the error was. The error was that it's a protic solvent. Having a solvent isn't a bad thing. Having a protic solvent, that's the bad thing with the Grignard because it's a strong base. Any questions about E? F. So here, I was hoping that you would recognize that your primary alcohol in the presence of the Jones reagent will become a carboxylic acid. So I wanted you to identify that these reagents, so having that water is what is going to make, this makes Jones, and Jones makes carboxylic acid. So that was the complete answer. So you should have had an OH there. Or it should have been, so if you said that it should be an OH instead of a hydrogen here, because of this makes Jones, or because this is a stronger oxidant, or this makes the stronger oxidant than PCC, so that gives you your OH. Anything along those lines of the fact that it's not PCC, you're recognizing what those reagents are making, and that that is a stronger oxidant to make the carboxylic acid, then that received full credit. Or if you said that you needed pyridine instead of water to stop at the aldehyde, then that was also received full credit. Or if you said that you need PCC to make the aldehyde, recognizing that, again, the reagents are the problem, that is the correct answer. Any questions about F? G. We look at this overall reaction. I see that my water is weak, a weak nucleophile, weak base. That tells me either SM1 or E1. Then I look at my leaving group is a secondary leaving group. It again tells me SM1 or E1. Cold is what tells me SN1. So I need to be doing an SN1 solvent or SN1 reaction. And when I look at this, the fact that I am doing a substitution reaction is indicating, or rather, sorry, what just happened to my brain? Start again. I look at the inversion of stereochemistry. And so the problem here is that this is just doing SN2. So that's what's wrong with this, is that I'm trying to do SN2 with our, with these conditions, either recognizing that the cold is favoring SM1 over E1, or that this is the weak nucleophile, and that you need to be doing SM1, not SN2. That's what I was looking for. If you knew that it needed to be SN1, then that received full credit. If you just said that you need to have a rearrangement, that was close because that's getting along the right lines. Like that is a problem, is that you would also need a rearrangement, but that's not the primary error. The primary error here is that we did the wrong mechanism, right? So if you took it from just a substitution standpoint of just look at my solvent is protic with the secondary leaving group, that told me SM1. Or if you took it from the weak reagent and then cold told me SM1, then that received full credit. If you had talked about the fact that you needed hydroxide instead of water, then that was only 1 point, because that's looking at, you're trying to, like, if you're trying to get to the strong nucleophile, like, you start to have issues of elimination getting in there, and that's not, like, our best solution, like, or not the primary error. I guess it is. No, you can have elimination competing. So then that's not going to be a good answer. So that's why I'd only receive partial credit. So I wanted you to recognize that you needed to be doing SM1, not SM2. That it was the wrong mechanism. That was the primary error. Any questions about G? H. For this one, again, we have the weak reagent telling us that it's SM1 or E1. Secondary leaving group, SM1 or E1. Heat tells me E1. So when I look at this, I am forming an alkene, so that tracks. But when I go through my mechanism, I would form that secondary carbocation and I can facilitate a carbocation rearrangement. So the problem here is not that I made the alkene here. The issue is that I didn't do the alkyl shift. I didn't make my most stable carbocation before having the base deprotonate. Because if there was no chance of rearrangement, then this would have been the correct alkene for the E1 reaction. The error is the lack of the carbocation rearrangement. It was the fact that you didn't make your most stable carbocation before having the base deprotonate. So that was the error with H, was you had to recognize that the rearrangement was missing. You're missing that alkyl shift. Any questions about H? I. So for I, we are looking at, we are trying to do a SN2 reaction. I know it's SN2 because I'm ending with this primary leaving group, or sorry, a primary substitution. So I am trying to have my chloride attack there and kick out the terp butoxide. So some people were saying that the sodium shouldn't be here. The sodium is still there. That's just a counter ion. That is the correct counter ion. So sodium there is fine. The problem is that alkoxide is a bad leaving group with the chloride being your nucleophile. So if you had said that like the reverse reaction is favored because this is the stronger base, or that the alkoxide is the bad leaving group, or like the O- is a bad leaving group, anything along the lines of like the products are more reactive, then that was the error, was that this is a bad leaving group, so this reaction does not occur because it's just the reverse. Any questions about I? J. So looking at J, I see that I have an alcohol with a strong acid. Sweet, I'm going to protonate something. So I'm going to end up with that oxonium ion and iodide and methanol. But here, I note that iodide, remember, is large. It is very large. So it does not have that tight solvent shell. So iodine is my best nucleophile in solution. Methanol is not my best nucleophile when I have that iodide because it has that negative charge and it is large. So iodine is the best nucleophile, or iodide is the best nucleophile to do this substitution reaction. So that was the error, is that the methanol needed to be the iodine because iodine is the best nucleophile. You use the wrong nucleophile in this reaction. Any questions about J? Cool. Question 16. All right, looking at our predict the starting materials. So I don't know if anyone noticed, but these are actually the they were originally predict the products in the summer exam that I gave you. Oops. And that we talked about in lecture. So they were the predict the products. And what I did was I just, instead of having it be a predict the product, I gave you the product and asked you what the starting material was. But even if you didn't know that, doesn't matter. We can still do it. Okay. So for this one, we are seeing that we end up with our why isn't this working? We have our alcohol and a tertiary substitution here. So I am imagining that with HBr that I would have protonated some oxygen in order to make it into a potentially good leaving group. And I would have had bromide as my nucleophile. So my retrosynthesis is what I'm imagining is that bromide, that was my nucleophile. So I'm going to imagine that I came from this potentially this carbocation. And then if I just try to imagine, okay, well, what starting materials would have gotten me there? I need to think about the fact that there are two unsaturations. Remember, unsaturations are either pi bonds or rings. I already have one ring. So then I end with one unsaturation. So I just start with one extra unsaturation. So if you try to put a pi bond in, then that would give you the correct product. So that's why I accepted it, but you haven't learned, well, at this point, you now know it, but at the point of the exam, you didn't know alkene additions. So I wasn't expecting you to do an alkene addition. If you did do it, because it would be correct, I did accept it. You did need to make sure you kept that dashed carbon, that stereocenter had to remain there because that is in the product. So it had to be there in the starting material in order to have that stereochemistry in the product. So I was not expecting that. So I was expecting you to think ring. So if I think about a ring that can be formed, well, if this oxygen is attached there, then that would give me this starting material, which would work to then have that protonated alcohol, and then that leaves, then your bromide can attack the carbocation to lead to your desired product. If you showed any stereochemistry at all here, literally anything was accepted. If you were missing carbons, then you got half credit. If you accidentally put your oxygen in the wrong place, you got half credit. If you drew 5 bonds to carbon, then you didn't get credit because it needed to be a real thing. Any questions about A? B. All right, so here I see that pyridine. Remember, pyridine is the poison that is going to turn the reagents into PCC. So PCC is my weak oxidant. So that turns my primary alcohols into aldehydes and my secondary alcohols into ketones. It is unable to make carboxylic acids. So that means my carboxylic acid had to be there to begin with. So this had to be there to start. And then I'm imagining that these will probably both be alcohols, but the molecular formula is what reassures me of that. So when I put those in to be the primary and secondary alcohol, that will give me the correct number of hydrogens. So if you left one of them as a carbonyl, then you wouldn't have had the correct molecular formula. Any questions about B? C. So for this one, I needed to identify that this is my only product. So that means that I need to be cognizant of where I'm putting my leaving group. So this, I see that strong base that's telling me I'm doing an E2 elimination. So I need to make sure that my starting material has the leaving group either opposite that methyl or as a 1,3 substituent. So I'm going to compare those two. The leaving group that I needed was given to me in my molecular formula. That's how I knew it had to be a chlorine. And when I compare these two, only the blue structure is going to give me this product, because now whether I take it on the left or the right, oops, if I take it from the left or the right, no matter what, it leads to this same product, this symmetrical product. Whereas this, or sorry, the symmetrical starting material will lead to that product. This starting material, I have alpha protons on both sides. So it will make that product, but it'll also make that product as its other major product under these reaction conditions. That is why it's incorrect. So the only correct answer was to have your leaving group here. And so that's what I was looking for, was I wanted to make sure that you saw that symmetry with that, so that if you take it from the left or the right side, that that's what led to the E2. There were some people that were picking their own favorite leaving groups. So if you put something other than chlorine, I did still give you half credit, because I thought the challenging, the significant part of this was recognizing the regiochemistry. So if you recognize the regiochemistry, I give you half credit. If you put the leaving group anywhere else, then that was wrong. Like I wanted you to see that the only way to get this product is if you have that symmetrical starting material. Any questions about C? D. All right, so for this, I am doing a two-step reaction. The first step I see is that PBr3 that tells me I'm going to go from an alcohol to a bromine, and it's going to happen via an SN2 reaction. And then the second step, I see that NaOH. And so because of the fact that I know I need to end with an alkene, that tells me that I must be doing an elimination, that E2 elimination, because it's a strong base. So when I consider this, I need to have my leaving group here or here. If I try to put it here as my alcohol here, then I don't actually have the reaction occur because I can't do SN2 on a tertiary leaving group. It's too sterically encumbered. So then my first step does not work. So that is not the correct starting material. I need to have my leaving group on that side. So then that means I needed to have this is my precursor. And the thing to note is I need to make sure that this bromine ends up that it is only antiperiplanar to this side because I told you it's your only product with this alkene. So I can't have it be antiperiplanar to this one. So I need it to be, or to the hydrogen on that side. So I need that bromine to be on a dash to make sure that it is going to be blocked by this wedged methyl because that hydrogen is on a dash. So then if it's not antiperiplanar, I can't do the E2 reaction. If that bromine is on a dash, then that means that I need this ethyl to also be on a dash because I need the wedged hydrogen in order to do that E2 elimination. So then I'm going to say, okay, so if this is that intermediate, this is the product of step one, then knowing that step one does an SN2 reaction, I had to have a wedged alcohol to get to the dashed bromine to get to this desired product. Any questions about D? Question 17, our syntheses. Yay. Okay, so for the syntheses, so I graded this section and you can see on the actual annotate, like the rubric that I gave you, the answer key and grading rubric, like this is a hot mess. That's because if you were right, then I still give you full credit. So even if it was not the answer that I thought of, so for example, these conditions also worked. So if you were correct, then you still receive full credit. Then I also had to modify it because when I was grading it, I was giving too many zeros. So then I went back in to try to give partial credit based on what I thought were like good answers. So like if you were like identifying the correct elements, identifying that you needed to do, like for this first one, recognizing that you needed to do a substitution and that you needed that SME, then as long as you recognize you need the sulfur, then that would get you partial credit. So I gave you 2 points if you recognize you had the SME. If you added it with solvent, then you got 3 points. If you did the thiol, which can be its own solvent, then that just alone got 3 points. If you wrote just MES without a charge and no hydrogen, then that was 1 point because that's not a real thing, but you at least recognize the right elements. If you did reaction conditions that didn't stop at having the correct leaving group, then you received half credit for that first component. So if you're adding acid, that's what gave you that half credit for that, the -1. And then if you're recognizing that dash leaving group going to the sulfur, basically, you know you have to do SN2 with the sulfur. That got you 2 points. And then as long as you had all aprotic solvents, then that got you 1 point. All right, so that's how we're assigning these partial credits, was looking at, did you identify the key reactions that we're trying to do? Did you recognize the right elements that we needed to have in it? And so that's all of like the extra annotations. So looking at how do I actually do this reaction? All right. So what I was hoping you would see is that I have this, we just kind of talked about it, but I have an alcohol going to the thioether. So I need to do substitutions. The fact that I see this stereochemistry retained tells me that I have to be doing SN2s. The fact that it's retained and not inverted tells me I'm doing 2 SN2s, because that's the only way that we can get this retention, is to do 2 SN2 reactions. So looking at that, I wanted you to do that OH to a good leaving group via SN2, either by using your phosphorus tribromide or thionyl chloride, or turn your alcohol into the sulfonate and then do that sodium chloride or sodium bromide or sodium iodide. Then that's what got you 2 points, was either recognizing good leaving group to then do the substitution, or using your one reagent that immediately does the SN2 reaction. That was the 2 points. Then the other 2 points, so this would have given us that intermediate, that then all I need to do is add my strong nucleophile. I wanted it to be SN2, so I wanted to make sure that it was a strong nucleophile with aprotic solvent. So I wanted negative charge for the strong nucleophile. Sulfur itself is already a strong nucleophile, but if you do the thiol, that is also a protic solvent. So that was losing points on the aprotic solvent front, but it would do the SN2. So you still received credit for the 2 points here. If it was protonated, you just lost points on the aprotic solvent part. And then as long as you had aprotic solvents, because you were doing all SN2, then that's what got you your full credit. So that was what I was hoping you would recognize and do for that reaction of what's different. I need to go from an alcohol to a thioether, and I need to do it via 2 SN2 reactions to retain that stereochemistry. Are there any questions about A? B, what I was hoping you would see is that we are doing an elimination. So I need to lose an alcohol, gain a pi bond, and specifically, I need it to happen on my less substituted side. I need to make the Hoffman product. So that means I need a bulky base to do an E2 reaction. So if you recognize that you're doing an E2 with a bulky base, that got you 2 points. If you were just trying to do E2, that got you 1 point. If you're just trying to do so E2 with a non-bulky, that was 1. If it was bulky but not E2, so it was like terbutanol, then that was only 1 point. That was half credit. The alcohol should have been turned into a better leaving group unless you were using the O- already, because if you start with O-, you can have O- as a leaving group. So if you did the terbutoxide directly, if you just did this step without making it a good leaving group first, then that gave you all 4 points from that. And then, or just, so if you just wrote KOTBU, that was +4. And then you needed to have a solvent in there, some sort of reasonable solvent. So either having that conjugate acid of it or any aprotic solvent, recognizing you're doing an E2, that's what was necessary. And then for whatever your initial steps were, as long as you were either doing like the trihalide, phosphorus trihalide or thionyl chloride, or turning your alcohol into sulfonate, whatever you did, then that worked. So if you used like triethylamine, that was your favorite bulky base, then that one needed an initial first step. You needed something to turn the alcohol into a good leaving group. So this would have only given you the 2 points from bulky base for E2, because that needed to have the alcohol become a good leaving group in order to facilitate that. So that's what I was hoping that you would recognize there, is needed to make the Hoffman product. So we needed a bulky base for an E2 elimination. Any questions about that? Two SN2 reactions was the key part of that one. C. Here, I'm gonna start boiling more water. I need more tea. Ugh. It's just a lot of talking. Okay, for part C. Looking at what is different, I am recognizing that I have this alkyne. This alkyne right now is going to be a strong nucleophile, strong base, because remember that this dissociates. So you get Li plus and that C minus. So I recognize that that is a strong nucleophile and a strong base. And what I see here is that there is that same carbon pattern. So I'm going to assume that this is what I'm adding in, and this is what I need to make. So if I recognize that I see this carbon-carbon bond being formed on one side, on the less substituted side, and I have oxygen on the other side, then I was hoping that you would see that this would be made from that epoxide via an SN2 reaction. So that was that nucleophile one side, oxygen the other, was what I was hoping you were identifying. And then recognizing it had to be SN2, opening on the less substituted side. And then in order to get this part, that ethyl, that was just another SN2 with your 2-carbon chain, because you would make the O minus after this adds in. If you did an acid workup after doing this to get to the alcohol first, then that was totally fine. I didn't take off any points. It was that received full credit. If you, oh, and then your last point was just making sure you had reasonable solvents. So all aprotic, whatever ones you picked, as long as they were aprotic, they receive full credit. In this last caveat, if you just did SN2 directly with already having an ether in there, that does work. So if you made your life even easier by just recognizing that this bond has to disconnect, so you just put all of that together and just put a leaving group here, then that was very clever, and that received the 4 points. And then for the 4 points for the structures, and then if you had aprotic solvent with it, then that got you your full 5. If you had the methyl here, so basically you did this, but you had the wrong carbon chain, then I just took off 1 point, because you were recognizing the key bond disconnection. So that's why I gave 3 points for that one. If you, a common error that was made was instead of having my epoxide, you tried to use the a ketone, but the problem with this is that then your nucleophile ends up on the same carbon as the oxygen, not on the opposite carbon. Also, this only adds 3 carbons, not 4. So there's 1, 2, 3, 4 carbons. So that was the other problem with this structure. So if you did everything correct to make this, so you did all the right solvents, then you received 3 points, because basically you lost 2 points for not recognizing you need the epoxide, but you received the 2 points for the alkylation, and you received 1 point for appropriate solvents. Yeah, that was the partial credits that were being awarded for part C. Any questions about that one? Part D. So here, I'm recognizing that this carbon scaffold is still the same. So what I need to do is I need to lose that bromine and I need to gain an aldehyde. So what I was hoping that you would recognize is that this carbon can be added by turning this into a Grignard. So if I make my Grignard from my alkyl bromide or bromoalkane, I can do that by just adding magnesium, or if you did lithium, whatever. I'm just trying to turn this into a nucleophile. And then I need to only add one carbon atom. So it needed to be that formaldehyde. So it had to be, come on, pen. That thing. Because you needed to be adding in just one carbon atom. So if you had like methyls here or anything else coming off, then you lost the point for that reagent. Then after a Grignard, you need to do an acid workup. And because I have to end with an aldehyde, ending with an aldehyde told me I needed PCC. Read it this way. That primary alcohol to aldehyde was PCC. And in the instructions, I told you needed all the complete set of reagents. So that's why you needed to actually write the complete set of reagent, not just PCC, not just the abbreviation. It was complete set of reagents. So it was the chromium oxide, HCl, and pyridine. If you wrote out pyridine, cool. It was these conditions were what you just need to write down there. If you did write PCC, because you were still recognizing that you had to do the oxidation, I did award half credit. So 0.5 points for that step. So you lost half a point for not actually following directions, but you were still doing the right thing. So, or on the right track. So then, still give you some credit. Yeah, I think that was the only real deviation for that one. Any questions about D? E. Ooh, water dinged. Hang on 2 seconds. All right, part E, we are recognizing that we are turning an aldehyde and a carboxylic acid into alcohols. So I needed to react on both sides. So indicating that carboxylic acid to an alcohol, that was telling me that I needed my strong reductant. So I needed that lithium aluminum hydride. So if you wrote lithium aluminum hydride, or LAH, you receive 2 points. It had to be aprotic because remember, lithium aluminum hydride is a strong base. So that needed the aprotic solvent for 1 point, and it was any aprotic got you the other point. And then because strong base, you must have the acid workup. So then you receive 1 point for HCl and 1 point for water, being water, the reasonable solvent, HCl being what actually gives you the protonated product. If you try to do sodium borohydride with methanol, that received only 3 points because yes, it is going to reduce your aldehyde, but it won't reduce the carboxylic acid. So that was not the reagents you needed in order to go from the carboxylic acid. The key indicator there was that's why you need lithium aluminum hydride. If you did the deuterium version, then that received -1, so that was half credit. Because that actually adds deuteriums in, you get one, stop it. You get 1 deuterium there and 2 deuteriums there. So if you deuterated it, then you received half credit because that doesn't make that product. Oh, and if you didn't number your steps, so some students just wrote all of these together and they just wrote this above and that below. Note that that does not mean 2 steps. Just because one's above, one's below does not mean 2 steps. Because here I have it above and below, and that's all 1 step. So it needed to be numbered. So if you didn't number it, then I took off 1 point. Right. Any questions about E? F. All right, so F was our hard one. So this was, well, I guess all of it was hard, but F was intentionally my hard question. So this was meant to be a, let's see if we can really be challenged and see, how we do with it. So this was one question that I anticipated would be hard, but totally doable. If we remember that this tautomerizes. So the key thing here is recognizing that OTBU is this part. So then, or potentially that part is actually, I guess I should do it this way, is that the tert-butyl is here. So then what I need to do is try to separate this, because this is that ether. All right, so if I have ROR, and this is a tert-butyl, and this is my allylic cyclopropyl. Oh, I put the alkene in the wrong place. There we go. Otherwise it doesn't tautomerize. So recognizing this, then I'm seeing that I need to get a tertiary substitution where I need to be adding that OME. So I needed OME, and I needed it to be on the more substituted side, indicating that I'm doing an SN1 reaction. So I need to make carbocations. So then that told me I needed strong acid. I needed my strong Bronsted acid, or you could have done strong Lewis acid. Nobody did, but if you did, it would have been fine. So if you did like BF3, or if you did AlCl3, that would have also given the 2 points. So if you did hydrochloric acid or sulfuric acid, that received the full credit. It had to be one of these two Bronsted acids because they both make non-nucleophilic counter ions. So because I'm in a protic solvent, chloride is not a nucleophile. Methanol is the nucleophile. So if you did HBr, then that received only 1 point for the acid because you would get some competition with the bromide. So what we would be doing here is we would protonate, we would form our carbocation, we would get here where the methanol can then attack, and then you would just do acid-base chemistry. But the key thing is that remember that this is an enol, and we had said our enols were not stable. So they readily tautomerized to just directly become the carbonyl. They go directly from that enol to the ketone. So there wasn't any other modifications. A lot of people were trying to do oxidations here. And if you tried to look at the ketone as your guiding factor, then you probably got lost and couldn't figure out a way to make the bonds work. The important thing was trying to utilize that tert-butyl. That's the key part that actually led you down a productive pathway for the synthesis. Right. There were a lot of different partial credits for this. If you tried to do methoxide, so you're trying to do an SN2, then that was a maximum of 3 points. So if you just gave OME minus without a solvent, then that got you 2 points because you recognized the correct elements that were being added, but you didn't have a solvent. If you did just methanol, then that got you your 3 points because methanol is a solvent. If you just wrote a, oh, right. So I ended up not doing this. So on my answer key, I scribbled this out because so many people did it that I went, just kidding. And I did actually give you 2 points if you wrote that, and then +1 for solvent. If you wrote methanol anywhere and you had absolute unreasonable steps happening everywhere, like nothing, basically, if you wrote the word methanol, but there's no way it would make that product, I still gave you 2 points. If you wrote methoxide, because this was really hard, I tried to give a lot of partial credit. So if you just wrote OME minus, and then, but there was no way you were going to make that product, you at least got 1 point. So I wrote methanol with nothing that actually makes it, 2 points. If you had a naked OME, so you just MEO by itself, with absolutely nothing that would make that product, then you got half a point because that's not a real thing, but you were still recognizing the right element. So I still tried to reward that. If you did, yeah, this was actually really clever. I don't know if if people knew that they were right when they wrote this, but I was really blown away by this. An alternative reaction that you could have done that I absolutely did not anticipate, was if you add tert butoxide with terbutanol. So you're adding that strong base with an O minus, you can have that O minus as a leaving group. So then you can do an E2 elimination. So the bond that we would break would be coming from this side. So there are way more beta hydrogens on that side. Also, this is where I can more easily access. So then that's what would lead to my Hoffman product. So if I take this proton, then that would make, oops, our enolate, which is that alkene with the oxygen on it, which would have been an alcohol, but it has a negative charge, so it's enolate, plus our Hoffman product, alkene, plus tert-butanol. So this, again, readily tautomerizes. It just directly becomes the ketone. So that took care of the one product. And then this, if you did an alkene addition, which again, I didn't expect you to be able to do an alkene addition, but if you did it, awesome. So that you did HCl and methanol, recognizing again that the chlorine is not going to act as the nucleophile because we're in a protic solvent. So your better methanol or better nucleophile is methanol. So then you would end up with the carbocation because your alkene attacks your acid, which is what we are learning, right now. And then the methanol is then what attacks your carbocation. And that did actually make that product. So that was that 5 points for having that terbutoxide and terbutanol or any protic solvent and methanol with hydrochloric acid. The other one that I was also really impressed by the ingenuity was I'm gonna squeeze it in over here. If you did HCl and water and then iodomethane and DMSO, because what that does so in that first step, you're again going to protonate your ether. You get your carbocation, then your best nucleophile, because chloride is not a nucleophile in protic solvent, that would then lead to your enol plus that tert-butanol. So you would go, I guess I'll actually draw it out. So you would get your enol plus that carbocation, and then water act as your nucleophile. And then you just needed to alkylate that alcohol in order to get it to be an OME. So if you did that with the MEI and DMSO or whatever aprotic solvent trying to do an SN2, then that made the other product. So then that received full credit as well. I was really impressed by that. That was not something I had considered. I like those bond connections. That was clever. Cool. All right. Any questions about F? Question 18. So these are our predict the products. And so we're trying to figure out what reaction we're doing for each of these. All right, I'm gonna do the left side first, and then I'll do the right side, because the right side, if you see, has all of that same starting material. So my hope, excuse me, was that you would recognize that the substrate isn't changing. So I just wanted you to see how our mechanism changes as we make our small changes to our reaction conditions. So as I change my reagent, or as I change my temperature, what that does. So that was my hope there. So we'll do the left side first, then we'll do the right side, because that'll be easier to talk about it as we're just doing those small modifications. All right, so for part A, methoxide, that is strong nucleophile, strong base. So that tells me SN2 or E2. I see my secondary leaving group. So that's again, SN2 or E2. I see heat, and that tells me E2. So I'm going to look for antiperiplanar hydrogens. So when I do this, I expected you to initially write E2, unless if you remembered the fact that we did this in lecture on the Monday before the exam. So if you remembered that, then cool. Then hopefully you just remembered that it had to be SN2. If you didn't, then hopefully you rationalized it out. That doing E2 requires antiperiplanar. In a ring, you can't have rotation. So if this is dashed, I need a wedged hydrogen. I don't have a wedged hydrogen. I only have dashed hydrogens. So because there is no E2 possible, now my only option is the one that was in competition. Remember, it is still a strong nucleophile. I could still do SN2. So SN2 is going to be my product. So because there's no antiperiplanar hydrogen, I cannot do E2. All I'm left with is SN2. So it's going to be my nucleophile tax, kicks out the leaving group. So I see inversion of stereochemistry with that OMe added in. Any questions about A? C. I see that, oops, strong base only. And that was that E1 or E2. The secondary leaving group didn't really tell me anything. I mean, it kind of told me probably E2. I don't remember what I actually told you on that chart. But the thing that was really reinforcing was aprotic solvent. So seeing an E2, or sorry, seeing the aprotic solvent told me I'm doing an E2. So I need to do that elimination. That is a small non-bulky base. So if I have beta hydrogens on the more substituted side, then if I can make this Zatsev alkene, I will. But I need to look for this leaving group. There are 0 beta hydrogens to the top left, but there are 2 to the bottom left. So the only way to do the elimination is from this left-hand side or bottom left, so that does that elimination. So because we are concerted, you can only take it from the side that has hydrogens. I only have hydrogens on this side. That's the only alkene that I can make. Any questions about C? E. So for this one, I was hoping you were seeing that potassium permanganate, that's a strong oxidant. That's our strongest oxidant. It turns our primary and secondary alcohols into carboxylic acids. And tertiary alcohol equals no reaction. So what I was hoping you would see is that we needed to oxidize this primary alcohol up to a carboxylic acid, and that tertiary alcohol would remain the same. And I was hoping you would see that step 2 was just trying to be an acid workup, because I had told you that when you're doing that potassium permanganate, you have that strong base, you need an acid workup as your second step. That being said, I should have written dilute here. in order to reinforce the fact that it was just an acid workup and not actually going to be doing an E1. If you did do an E1 in the second step on that side, then that received full credit. So I was hoping you would just see the potassium permanganate, tertiary alcohol stays the same, primary alcohol goes to carboxylic acid. But since I didn't make that dilute, if you tried to do an E1 as well, then that you receive full credit for that too. As long as you did the E1 making the most substituted alkene. Right. Any questions about E? G. All right, we see our sodium borohydride. That is going to be our reductant. The methanol is a reasonable solvent. That's what's going to actually protonate our alcohol. So this adds to carbon of the carbonyl. The hydrogen makes it the alcohol of the methanol. So you go from O- to OH. The sodium borohydride is our weaker reductant. So it only works for our aldehydes, ketones, and acid chlorides. So it turns our aldehyde, ketone, or acid chloride into our primary alcohol or secondary alcohol, depending on if you started with 2 carbons or not. So ketone went to secondary. So seeing that aldehyde became a primary alcohol, carboxylic acid cannot be reduced by our sodium borohydride, so it stays a carboxylic acid. If you wanted to reduce the carboxylic acid, you needed lithium aluminum hydride. Any questions about G? I. All right, so now I have my lithium aluminum deuteride. So this, if it was LiAlH4, then that would be adding hydrogens to my carbon. But I have deuterium, so that shows that my deuterium is what is adding to the carbon of the carbonyl. And then my acid workup, this is what protonates the alcohol. That's what turns the O- into OH. So that's why it had to be a hydrogen. So step 1, put the deuterium. Step 2, put the hydrogen. So that's why it had to be that product. Any questions about I? Hey. So this was our mesylate. So whether if you recognize that that's the CH3 makes that mesyl chloride, then sweet. Otherwise, if you just drew it out, then you would see that you have that good leaving group. Your nucleophile is going to be the oxygen. Remember that only the electrophile sees inversion of stereochemistry. So that is going to retain stereochemistry because it's my nucleophile, so it stays a wedge. So if you wrote it as OMS, or if you recognize that, or rather just drew the structure, or if you wrote the condensed form, whatever, all of that was accepted. The triethylamine, the one equivalent of that deprotonates the alcohol. So that turns your the oxonium ion into the neutral, so it just acted as a base. The DCM and cold was trying to hopefully reinforce that we're doing an SN2, but remember, only the electrophile sees inversion of stereochemistry. The nucleophile does not. Any questions about K? All right, let's talk about the structure. So again, I was hoping that you would have recognized that putting the double bond right here is never going to be an option because I told you that on the other page. So hopefully you never drew that thing, or having it like that. This is wrong because of what we already talked about in question 13. So E2 required the antiperiplanar. This is not antiperiplanar. E1 is going to always make the E not our Z alkene. So these were never products, because these are the E alkene. Or no, sorry, these are the Z alkene. So we had to make our E alkene if we're going to draw the alkene on that side. All right. So then we're going to go through this and we see all the slight modifications. So I see weak nucleophile, weak base. That tells me SM1 or E1. Then I see my secondary leaving group. That tells me again, SN1 or E1. It doesn't help me. Cold is what tells me SN1. So that was the deciding factor. So in SN1, leaving group leaves. You get your carbocation. You must make the most stable carbocation before anything else can happen. So because there is this tertiary hydrogen next door, you get the hydride shift. As soon as you make that carbocation, you destroy any stereochemistry that you had. So now that is planar. So there is no stereochemistry there. So that's why there's no stereochemistry in the product, because then water attacks, and then you just do acid base, and that leads you to your product. So that was the product of the first one, was recognizing that you had to have your hydride shift. It was SN1, and you lose stereochemistry. If I'd had it be hot, so same consideration of SM1 or E1, but then I get down to heat. Heat told me E1. So E1, I get again to that rearranged, I make my secondary carbocation, it rearranges to make my tertiary. Now, these are both propyls, so they're the same, whether you look at the left or the right. But so I'm looking at the fact that I have these two CH2s. These are equivalent. There is nothing differentiating that left or right side in terms of number of substituents. No matter what, I'm going to end up with a tri-substitute alkene. So I get both tri-substitute alkenes. You must make sure, though, that you have it rotated to get the E alkene. So if I make the double bond here, these had to switch first in order to get my E alkene. I can't make the Z alkene. And then the other was recognizing that once you make that carbocation there, that it could form on the right-hand side. So then that led to that product. Yeah, so you need to see both tri-substituted alkenes. Any questions about B or D?
Wait, so why do you show the other one again? Sorry.
Yeah, no, you're good. That's why I was checking. Cool. So the fact that this hydrogen is on that CH2 and this hydrogen is also a CH2. So no matter what, I get a tri-substituted alkene. So because they're both tri-substituted, they are equally as stable. So what E1 was saying is that you're always going to make the most stable alkenes. You're always going to make the most substituted, the Zatsev, and you're always going to make your E alkene where your big groups are as far apart as possible. So the fact that both of them are tri-substituted means that we make both of them. So that's why we needed to have the two products there, was because no matter what, you end up with the tri-substituted. So they're both the Zatsev product.
Thank you.
Looking at F and H. So F, I now see that it is strong, the strong nucleophile, strong base. And again, so that tells me SN2 or E2. I see the secondary leading group. Again, SN2 or E2 doesn't help me. Cold tells me I'm doing SN2. So SN2 means I need to have that hydroxide, do the backside attack, kicks out the chlorine. So you end up with the dashed alcohol on that carbon. So then you just kept everything else stayed exactly the same. And you just need to have that inverted stereochemistry on that carbon. For our next one, again, I'm the strong, still secondary, but now I'm room temperature. Room temperature tells me E2. So E2, I need to look for my antiperiplanar hydrogens. So if I have hydrogens on the left or the right, I see that I have antiperiplanar hydrogens, or I guess I should say beta hydrogens on the left and the right. If I rotate it, both of them could be antiperiplanar. Hydroxide is non-bulky. Non-bulky tells me that I'm going to make my Zatsev product. So I need to make my most substitute alkene. So the non-bulky told me that I'm taking the hydrogen on the right-hand side. So I need to get it to be antiperiplanar. So I have to rotate this. So it's what we did before. So I need wedge to go to dash. So the hydrogen's now on the dash, antiperiplanar to that chlorine. So wedge went to dash, dash goes to line, line goes to wedge. So now I can do my E2 elimination because now I'm antiperiplanar. So now I see that I have my ethyls are on the same side. The propyl is on the opposite side. That makes my E alkene. When I look at the tert butoxide, that strong base, my strong bulky base, I was hoping that you're recognizing that now we're going to make our Hoffman product being bulky. So we're going to take it from the left side. Just take whichever hydrogen, because there are two hydrogens. I don't have to check for the antiperiplanar. I will just make the alkene that is most stable. I will make the trans alkene. So I'm just going to take the dashed hydrogen because my bonds are already opposite. So I just needed that O TBU minus. Takes that, that kicks out, that goes out. So then that does the Hoffman elimination, making the trans product. Any questions about F, H, or J? For L, we see that the carboxylate is going to be a strong nucleophile. So this is nucleophile only and strong nucleophile because it's negatively charged. It's a nucleophile only because it's resonance stabilized. So that's why it's not going to act as a base. The benefit of doing this SN2 followed by ester hydrolysis was that it avoids any E2 in competition because I don't have a base. I just have a strong nucleophile. So I'm going to do SN2 where I get my carboxylate, comes in, kicks that out. That makes my dashed ester. And then that second step was that ester hydrolysis that broke this apart to give you your alcohol. Now it stays a dash, or sorry, it became a dash because of the first SN2, and it stays a dash because the next step is just deleting that carbonyl. Any questions about L? Cool. So that's what I was hoping you would see on the right side of 18, was the fact that we're just doing weak nucleophile, cold, SN1, weak nucleophile, weak base, heat, E1. Then when we get our SN2, what does SN2 look like? What does E2 look like with a non-bulky, E2 with a bulky? And what does our ester hydrolysis do? It just gives us our SN2 product. Okay. 19. For part A, This is the exact mechanism that I did in lecture. That was also in the book. So even if you didn't remember that or didn't attend lecture, so you didn't know, we can still absolutely do it. So remember that we need to rationalize the products that are being formed. You do not get to use any other reagents than the ones that are given. This is what you must use. So strong acid, protonate something. The most basic site comparing oxygen and sulfur, oxygen is smaller, so it's the stronger base. So oxygen is what we're going to protonate. So that oxygen lone pair is what takes the proton. We break the hydrogen-oxygen bond, give the electrons to oxygen. And that makes the hydrogen sulfate byproduct and our protonated product. The fact that we see that I go from a 4-membered ring to a 5-membered ring is telling me that I need to do an SN1 reaction. So I knew it was substitution because I'm going from the alcohol to a thioether. So one functional group to another functional group. The ring size changing tells me rearrangement. So rearrangement tells me, so small ring, small to large ring. Oops. Equals rearrangement. Rearrangement tells me SN1. So SN1 is telling me I got to make sure that I make a carbocation, do carbocation rearrangement, and then have the nucleophile attack. When we were trying to track our bonds, in lecture, I had told you to try to anchor onto your product. So recognize, I saw those 2 methyls and I saw that that was there, telling me this carbon is probably that carbon. I'm going to try to make that the case. It might not be. We might have to do more stuff, might have to do more rearrangements, but that's my hope. So then when I'm looking at that, if I number this 1, 2, 3, 4, 5, then I'm hoping that this is just going to be 1, 2, 3, 4, 5, recognizing that I need to break the bond between 2 and 5. So this bond is broken. This bond is broken. And I need to make the bond between 1 and 5. I need to make this bond. So I got to find a way to make those connections happen. And then in the end, I'll also add sulfur. All right, so we did strong acid, protonate something. Then we get to our oxonium ion. So now we have a good leaving group. Now we're ready to do our first step of SN1. So this was, we did acid base. Then we did leaving group leaves. That makes our carbocation. So at this point, I now need to rationalize some rearrangement that's going to happen because I can't have my sulfur attack right now because that doesn't give me that product. So while I have the carbocation, that's when I'm going to do my rearrangement. So now is the time to break that carbon-2, carbon-5 bond and make the carbon-5, carbon-2 or carbon-1 bond. So I do that by having that arrow. That is my alkyl shift. And so we had said that it does not make a more stable carbocation, but it makes the more stable molecule. So that's why it happens. We're releasing ring strain. Also, it's necessary to get to that product. You had to make a 5-membered ring. This is how we do it. That's how we can make that happen. So we do our alkyl shift, starting from the bond, going to the carbon. Then our next step is going to be now nucleophile can attack. And then you just have to do acid base to get it neutral. The best base in solution was water because you have the oxygen, which is smaller, so it's the stronger base. Any questions about A? For B, this was that mechanism that I emphasized in lecture, or at least tried to try to say that it was really important and really powerful because this was that reagent that turned our alcohol into a halogen. Also, I was hoping that you would recognize that when you're doing the synthesis questions, or the There was something else. Was it multiple choice? I guess it was really synthesis is where I was hoping that you would recognize that, like, that's how I turn my alcohol into a good leaving group. Oh, and the open-end one, the what's wrong with it, that you don't use the sodium chloride, you needed to use the thionyl chloride in order to actually do that SN2 reaction. Okay. Well, I guess that wasn't the what's wrong with it. The error was in ether. Yeah, that doesn't work. Whatever. So hoping for synthesis was how it would help you. That turn alcohol into a good leaving group, that's thionyl chloride. Okay. So when we think about our mechanism, the most people were okay getting to the chloride, that you were okay making this first product. But I told you you had to do all given products. You had to figure out how to make these byproducts. The reason that I wanted you to show me how to make them was because remember I said that that was the, like, this was the powerful part of why this reaction is happening. The driving force is that I am making gases. I'm making that byproduct. That is the driving force. That's what's actually happening. So that's why I wanted you to be able to draw that mechanism. So, first thing is drawing out just the structure of thionyl chloride. So that is our, that's weird. Having the sulfur with a double bond to oxygen, 2 single bonds to chlorine. This is an electrophile. I recognize it's an electrophile because that chlorine's a good leaving group. So that makes my alcohol my nucleophile. So I'm going to go from the lone pair on the oxygen to the sulfur, kick out my leaving group. If you, I don't think anybody did this, but if you did, you receive full credit. If you did an addition elimination reaction, so if you try to treat this like a carbonyl, which if you have me for Orgo 2, this is actually the mechanism that I'll want you to do. Because it's carbonyl chemistry, is that you would push the electrons up onto oxygen, that's doing an addition, and then you get sulfur, double bond O, no, sulfur, single bond O, Cl, Cl, that's O minus. So then the O minus falls back down, kicks out the chlorine to do the elimination. So if you did this instead of the SN2, this also received those +2 points if you did it correctly. I don't think anybody did. But if you did the addition elimination thinking that it was acting like carbonyl, cool, good job. That received full credit. I was just expecting you to try to do an SN2, recognizing you have a nucleophile, good leaving group. And if you're wondering which one's more accurate, they're actually both reasonable mechanisms. I have not seen any data. Last time I checked, I think was last fall. But I haven't seen any recent data talking about one mechanism being better than the other. Because sulfur is larger, it is actually able to do the SN2. Like there is data to indicate that both are possible. So it seems to be like really substrate dependent as to which one is going to happen. So both of them are reasonable arrow pushes. Or at least from the last time I checked. Okay. So we did SN2. You did nucleophile, attach your electrophile, kicks out your leaving group. Now I have chloride and I see that this oxygen is positively charged. So that whole thing becomes my leaving group. So now I can do another SN2 reaction where my nucleophile attacks the carbon because the oxygen has a full octet. So remember when you have a full octet, you attack next door, not the oxygen atom directly. You attack next door, give the electrons to oxygen, kick out your leaving group. And that makes your chloroethane and this byproduct. So that cleaves that bond, giving you that product. So then the last part of this hurdle is just figuring out how do I turn this into those gases. So I need to break the sulfur chlorine bond. I need to make an oxygen sulfur double bond, and I need to break that hydrogen oxygen bond. So this was the steps that I showed you where the lone pair comes down and it pushes the chlorine out. And then that chloride, I said, the only reason this is the only time, and I tried to emphasize, is the only time we will ever use our conjugate base of a strong acid as a base. And that's because there's literally nothing else around. That's my only option. And I need to make hydrochloric acid gas. So that's why chlorine here, or chloride, is acting as our base to do that final deprotonation irreversibly, because these are making gases. Any questions about B? Cool. So then for 20, this was just, the bonus was just, do you know what these common reagents are, or sorry, solvents are for the aprotic solvents? So for the acetone, that is propan-2-one. So we said the common name was acetone, but it is propan-2-one, so it's that thing. Acetonitrile is the methyl nitrile. So that's that thing. DMF is our dimethyl formamide. So that was our nitrogen had 2 methyls, and then you had that aldehyde, but it's actually an amide functional group, which is why it ends in amide. And then DMSO is dimethyl sulfoxide. So that's where it's our essentially acetone, but with sulfur instead of carbon. And then for 21, it was just as long as you listed anything that related to organic chemistry, you receive that point. So yeah. Any questions about 20 or 21? Any questions at all about anything now that we've gone through the exam? Okay, cool. Well, hopefully it all makes more sense now as to why those answers are what they are. If you do have any questions, please do ask. You can ask on Teams, sending email, in office hours, before or after lecture, in my office hours, the TA office hours, in recitation. Ask. Don't just sit wondering. Ask. I want to make sure you fully understand this content, because it really is fundamental to being able to, you know, move on through the rest of organic chemistry. Like it's 2 of the 3 main reactions that happen in organic chemistry. So when you get to Orgo 2, we're going to assume you are a master of all of this. And when you get to biochemistry, you'll still need it. If you take carbohydrate chemistry, you need it. If you are basically doing any job that is relating to just like chemistry or biology, you need it. If you're taking the MCAT, the DAT, or a GRE, then these are definitely going to be questions that come on it. Yeah. So if you're not sure, ask. I want you to know the answer. All right. Are there any last minute questions? All right. If not, then thank you to those of you that hung out with me this whole time. And I hope you have a wonderful night, a good weekend, and I will see you on Monday.